Hello everyone, I'm Dr. Fawzul Atiq. I'm giving some series of lecture on the course Probability and Statistics. Today we are going to discuss about a new concept called random variable. This concept is easy, but if you just look at the definition, it is a bit difficult to understand. So what we'll do, we'll first discuss few examples and then slowly we'll move into the definition of random variable. Consider this example. Rolling of two dice. Now, in the experiment of rolling two dice, consider the event E that the sum of the dice is 7. Now, this experiment we have already discussed and then we already found its probability of this event E. Correct? Now, here we are interested is in the sum of the dice, right? That whatever the two dice we have rolled, then what is the sum of them? We are interested about them, not the actual outcomes of the individual dice. See, the actual outcomes of this event are what? It is 1, 1, 1, 2, 3, 1, 3, 2, all that 36 outcomes we have, right? We are not directly interested in that. We are interested in the sum of the two dice. Correct? So we are thinking about a new variable. It is the sum. And in this question, it is the sum of the dice is 7. But why only it is 7? One can also ask that G is the event that sum of the dice is 5. Possible. Another event is sum of the dice is 11. Possible. So we are thinking a new one which is related to the individual outcomes, but which is not the actual outcome. We are interested in the sum of the dice. And therefore, once the two dice are rolled, let the variable x denote the sum of the dice. Let the variable x denote the sum of the dice. So we define a new variable which is x, which says that the sum of the dice is. Therefore, the event E is the x equal to 7, and therefore the probability of the event is P of x equal to 7. Now, in the event I discussed now that suppose H is the event that the sum of the dice is maybe 11. So in that case, P of H is what? P of H is equal to P of x equal to 11. Correct? So we made a new variable. Let us have another one. Just let me change the color of the pencil. Just a second. Okay. Now we have another experiment. Tossing 4 coins. In the experiment of tossing 4 coins, consider the event F that the outcomes has at least 2 heads. Right? So we are tossing 4 coins. Then an event. So then we are having how many total number of outcomes in that experiment? We are tossing 4 coins. Each of them are having, each of the coins will give you 2 choices, right? Either head or tail. So there are 4 coins we are tossing. So how many different type of outcomes we'll have? We will have 2 to the power 4 number of outcomes. Now here we consider the event F that the outcome has at least 2 heads. So which is not exactly the outcomes, right? So here we are interested in the number of total heads, not the actual outcome of the individual tosses, right? So number of total heads. And suppose we define a new variable that y is the number of heads in the 4 tosses. In the experiment of tossing a 4 coins. Suppose y is the number of heads. Then according to this event F, it is the outcome has at least 2 heads. Therefore, we are discussing about the P of F equal to P of y greater than or equal to 2. Because y gives you the number of heads. Similarly, if let's suppose G is an event that outcome is 3. right? Number of heads is 3 in this experiment. Then P of G is what? P of G is equal to, with this variable, we can certainly mention it, y equal to 3. Correct? Okay, let us discuss another experiment. Selecting balls from an urn. 4 balls are randomly selected without replacement from an urn containing 20 balls numbered 1 to 20. So you have an urn, correct? Where you have 20 number of balls, you have 20. Now each of them have some leveling, like ball 1, ball 2, like that, ball 1, ball 2, like that. Each of the balls are labeled 1, 2, 3, 4 up to 20. Now from there, what is the experiment? 4 balls are randomly picked. So you picked 4 number of balls from this urn without any replacement. Now consider the event G that out of the 4 selected balls, the largest number is 10. Now we consider an event G that out of these 4 balls, selected ball, the largest number is 10. So one of the ball should have number 10. And should be the largest number. So this is our experiment and G is that event. So here we are interested in the largest number ball, right? Not that actual the outcomes of having 4 balls, because how many ways you can do it? 24 ways you can select the 4 balls from the 20 number of balls, right? So each of the outcomes are like that, 4 balls, but we are not actually interested in all these 4 ball. We are interested in the largest number ball in each selection, right? And in this case the event G is the largest number should be 10. So let us define a new variable. Let Z be the largest number among the 4 selected balls. We define a new variable because we are interested in the largest number one. Because we may be interested in largest number ball, maybe 15, largest number ball maybe 20, anything is possible. So this event G is P of G equal to P of Z equal to 10. Right? Now if somebody said that, okay, let's suppose if be an event that it is the out of the 4 selected ball, the largest number is 12. Then what is the probability of this event? P of A, we can certainly write it as P of Z equal to 12. Correct? So in all these example, we were interested in a variable whose values is dependent on the outcome of the experiment. And we did not care about the actual outcomes here. Right? Like the first experiment, we interested in the sum of the 2 dice. In the second experiment, we interested in the number of heads in this rolling of 4 coins. In the third experiment, we are interested in the largest numbered ball, right? So we are interested in a variable which is dependent on the outcome of the experiment. So these quantities of interest are known as a random variable, right? By defining this random variable, we can even generalize this thing, that we are interested in the sum. First example, the sum was 7, but why it is 7? It can be whatever the sum possible, all values we can take, right? So we define a new variable. So these kind of variables are known as random variables. Now let us have the proper definition, mathematical definition. So given an experiment whose sample space is S, a random variable x is a real valued function defined on the sample space S, and it is from S to R, real number. Now see, in the first experiment, right, in the first experiment, that rolling 2 dice, we said x equal to 7, right? We said x equal to 7. What is that? X was the sum of the 2 dice. So x is equal to 7. So few of the outcomes was there which are in the sample space. That who are this 7? Okay, suppose x equal to 2 in that experiment of rolling of 2 dice. X equal to 2 means what? That sum of the dice is 2. Therefore, you actually says that X of what are the outcomes? It is 1, comma 1. Of this event is actually 2. Right? X equal to 3. It is what? It is that. So X is taking some outcomes from the sample space and it is giving some value that, okay, 3. So in this case, the domain is the sample space. Domain is the sample space S and range is the real number. Because this sum can be 2, can be 3, can be 4, can be 12. All of them are real numbers. But these are taking some of the outcomes, right? So X equal to 3 if I have, that means what are this event? It is maybe 1, 2 and the event 2, 1. So these are the outcomes from the sample space. For them, this value gives you 3. Right? So given an experiment whose sample space is S, a random variable X is a real valued function defined on the sample space S. And it is a map from S to the real number set. I hope. So mathematical definition is a bit difficult to understand, but you understand that you are defining a new variable depending on your experiment. Correct? So we'll do a lot of examples so that random variable concept will be very clear to us. Now, variables, random variables are of two types. One is discrete random variable, another one is continuous random variable. Right? Now, this discrete and continuous, this concept all of us know. So, discrete means which you can discretize, that which are different, that things are different from each other. These are the discrete points. It can goes up to infinity. That's fine, but still you can separate them out, right? And continuous means that you will have this kind of thing. How many, suppose here how many points are there, you can certainly count 1 2 3 4 5. You can go, it can go up to infinity, that's fine, but still you can count. But how many points are there in this interval? You cannot count, right? So these are the continuous value points. Now, till now, the random variable we discussed in the first example, we had that x equal to 7, x equal to 3, 2. These are the discrete type, right? So all the example, whatever we have discussed here, all of them are the discrete type random variable. So a discrete random variable takes a countable number of distinct values. It typically arises from the experiment where outcomes are finite or countably infinite. So it is outcomes are finite or countably infinite. Right? So this kind of random variable are called the discrete random variable. So countable number of distinct variables. If it is finite, definitely it is countable. If it is infinite, it should be countably infinite. That means you should be able to count it. We'll discuss some of its experiment. Yes, the examples are the number of heads in 5 coin tosses. So we have the experiment is you are tossing 5 coins and a random variable is the number of heads. Right? So in that case, that random variable can take the value like 0, that no heads, or 1 or 2 or 3 or up to 5, right? Sum of the two rolled dice in the another event. We have already discussed this one. So that x can take some real number values, right? So they are the 2, 3, 4 up to 12. Similarly, the number of customer arriving at a shop in an hour. So these are all the random variable you can define where it will take the discrete type points. So all of them are distinct values. So you can able to count them. Look at this experiment. The number of heads in the experiment of flipping a coin at infinite number of times. So you are flipping a coin infinite number of times. And your random variable is the number of heads in that experiment. So in this case, suppose x is the number of head in that experiment. X is the number of head in this experiment. So what values x can take? So even it is infinite number of experiments, x can take the value 0, no heads, or 1, or 2, or 3. So in that way, how much it can go? Because you are tossing the coin infinite times. So how many times head can appear? It can be 0, 1, 2, 3, and it can goes up to infinity. Right? So it is infinite, but it is countably infinite. Right? All of the other three cases, it was the finite one. So these are the examples of discrete random variable. Now look at this example. This definition, continuous random variable. So as I discussed, that continuous means that you cannot able to count even. Right? If you have even a small interval 0 to 1, you have this. How many points are there in this line between 0 to 1? No, you cannot. Even from 0 to 0.1, how many points are there within that? You cannot count. So they are the continuous time. So a continuous random variable takes an uncountable number of values within an interval, right? Uncountable number of values within an interval. These variables usually represent the measurement. Till now, we have not discussed any of the events, but we can certainly bring few of the experiment. Look at that, the height of a student in a class. See, suppose you have a class and your random variable says that the height of a particular student, right? So x is the random variable, it is the height of a particular student. So what values this x can take? Suppose in the class maximum height is 140 centimeter and the maximum height may be 185 centimeter. Suppose. So this x can take any value between them. Correct? So it is 140.01, 140.005, 140, 146.753423. Any value it can take. So it is in continuous time, right? So you uncountable number of values it can take, that value x. Right? So this x is a continuous random variable in this case. Again, the time required to complete a task. Suppose y is a random variable, that is the time required to complete a task. And suppose the time is 2 hours to maybe 6 hours. But within this 2 to 6 hours, any kind of time y can take. So you can have the microseconds, nanoseconds. So you can divide the seconds also in infinite number of times. Right? So it is uncountable again. So again, y is a continuous random variable in this case. Clear? That similarly, temperature in a city on a given day. So the temperature can be anything. So from 24 to 36, suppose, in one day. But this temperature can be anything. So it is uncountable again. Similarly, lifetime in hours in the experiment of measuring the lifetime of an electronic device. So electronic device, what is the lifetime of it? So again, it can be 0 to any number of time. So uncountable. Right? So this continuous random variable part we'll discuss later. First, we'll finish some content on discrete random variable. Now again bring the same experiment, that rolling two fair six-sided dice. Then what are the sample space? We know that it has 36 number of outcomes, 1 1 1 2 1 3, like that, 2 1 2 2 2 3, all these 36 outcomes we have. And x is the sum of the numbers on the two dice. Then x is a discrete random variable. Yes, definitely, because you can certainly, they are the finite numbers, distinct numbers. Now you tell me what are the values x can take. X is the sum of the two dice, right? So x value will start from 2, that is this event, minimum 2, because both the dice will have 1 1 face. Then it can take value 3, 4, any value it can take. It can take 12, it can take 13. Can it take 13? No, not at all. How can it be the sum of the two dice is 13? It is not possible, right? So this is not at all possible. Therefore, we'll have the x can take only these values which are from 1 to which are from 2 to 12. So x is a random variable. And then we can be able to find the probability of each of these random variable, which are different event. Right? So P of x equal to 7 in our calculation, it was 6 by 36. We have already discussed in some of our lecture this experiment, because this 6 pair can have in this outcome. So 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So 6 number of x equal to 7 means sum of that event is sum of the dice is 6 divided by the total number of. So sum of the dice is 7. So there are 6 number of outcomes. Number of favorable cases for that event is 6 divided by total number of outcomes. It is 36. So x equal to 7 is 1 by 6. Similarly, p of x equal to 2 is what? So it is only outcome where the face value is 1 and 1 in both the dice. So probability of that event is what? 1 divided by total number of cases. In same way, we can find the probability of each of the event. P of x equal to 3, x equal to 4, x equal to 5, up to x equal to 12. And you note that this x values, whatever it takes, this will give you the complete sample space. If x equal to 2, that means 1, 1. X equal to 3 means 1, 2, 2, 1. All the outcomes is covered within this, right? So that part you can just keep it as a note. We'll just bring it back again. Okay, look at this example. Tossing 4 pair coins. We already discussed now. So then the sample space is all the 2 to the power 4 outcomes, that head and tail, all possible combinations. 2 to the power 4 number of outcomes you have if you toss 4 coins. Then y is the number of heads. This is the random variable. Then y is a discrete type. And what values y can take? So you are tossing 4 pair coins. Y is the number of it. So it can be 0. Number of it can be 0. Number of it can be 1, 2, 3. Or number of it can be 4. Right? And then we can, the question was that some event we discussed, right? That was the event that it is the number of head is at least 2. So in this case, P of y greater equal to 2. Now, we already seen that these are the complete list of outcomes. That is the whole sample space. So our sample space S is equal to, basically, these are the events that y equal to 0, union, y equal to 1, union. These are the cases, y equal to 2, union, y equal to 3, union, y equal to 4. This is the whole sample space. And all of them are mutually exclusive type. So these are all mutually exclusive. These are basically y equal to y for y particular value. It's some event. Y equal to 1 is another event. So all these events are mutually exclusive. So probability of S is the probability of their sum. P of y equal to 0 plus P of y equal to 1. Like that we have P of y equal to 4. But P of S is equal to 1. We already know. So this is this value. P of y equal to 0 and that. Then P of y greater equal to 2 means what? It is 1 minus, right? So we have P of y greater equal to 2. It is basically 1 minus P of y is less than 2, which is 1 minus P of y equal to 0 minus P of y equal to 1. So this is happening because of this reason, that S is the sample space, is the all random variable, whatever values they are taking, it is actually giving you the sample space, and they all of them are mutually exclusive. So by the axiom 3, we can say that probability of S is their individual probability sum, but probability of S is equal to 1, that is from axiom 2, and therefore the whole probabilities of this sum is equal to 1. So probability of y greater equal to 2 is basically 1 minus p of y less than 2, and this will give you this value. I hope it is clear. We'll discuss this probability in some other res- lecture. Now, this experiment, suppose that our experiment consists of tossing three fair coins. If we let y denote the number of heads that appears in these three tosses, then it is a discrete random variable, and in this case, what value y can take? Number of heads in a tossing of three pair coins. So y can take the values as 0, 1, 2, or 3. And this is the complete list of random variables, right? Now, probability calculation we can do. So what is P of y equal to 0? P of y equal to 0 means it is the event that where number of head is 1. Sorry, is 0. Number of head is 0 when you are tossing three coins. So it is that means what is the sample space? Sample space was like this, na? H, 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 T, H, T, H, T, H, H. Remember, we have already discussed this example. Let dot, 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 T, T, T. So P of y equal to 0 means what? That means number of head is 0. So you have only one such case, and total number of outcome was 8. So P of y equal to 0 is 1 by 8. Similarly, P of y equal to 1 is what? That means number of head is 1 whenever you are tossing three fair coins. So you have only three cases like that. So it is probability of y equal to 1 is 3 by 8. So in this way, you can calculate P of y equal to 2, P of y equal to 3, all this. To each of the random variables, particular value are basically some particular event, and we can able to find their probability. Correct? So yes, that's what we have discussed. P of y equal to 0 is 1 by 8, P of y equal to 1 is 3 by 8, y equal to 2 is again 3 by 8, and P of y equal to 3 is 1 by 8. And if you just add them up, you can see that 1 by 8 plus 3 by 8 plus 3 by 8 plus 1 by 8. This is actually giving you the number 1. Right? So probability, therefore, we all have already seen that this is actually the sample space. Y equal to 0, 1, 2, 3, union of all such event, y equal to 0, union y equal to 1, it is the actual sample space. And therefore probability of their sum is equal to 1, that we have already seen. Okay. Now look, again come back to this experiment, that 4 balls are randomly selected without replacement from an urn containing 20 balls number 1 through 20. So we have 20 balls in the urn, and each of them have some number 1 to 20. And we were interested about the largest number of ball. So suppose X is the largest number ball among the selected ball. Then X is a random variable and it is a discrete type. Can you think that what values X can take? So you have 20 balls in the urn. You have selected 4 balls among them, and among these 4 balls, so you have selected 4 balls among them, and among this selected ball, largest number is X, right? So what values X can take? X can take the value 20, so largest number ball can be 20. X can take the value 19, X can take the value 10, X can take the value 5. Can X take the value 3? Not at all, right? So even if you have the very like the all first 4 you have taken for all the first 4 ball 1, 2, 3, 4. So even if it is 1, 2, 3, and 4, till you will have the number is minimum 4. Maximum number is minimum 4, right? So the even the if you take the first, so X can take the value 4, then it can take 5 or 6, it can take any values up to 20. right? Because all the four balls have some number, so in the minimum case it should be at least four. This at least in this selection. Other than that, it can goes up to 20. So x can take all these values 4, 5, 6 up to 20. And then for I greater equal to 4, what is the probability of x equal to I? Think of this example. What is the probability of x equal to I? So x equal to I means that among these four selected ball, the largest number is I. What is this probability? See, before discussing this, I want to discuss that what is the probability of x equal to 5. It means what? That among these four ball, I have the largest number ball is 5. Right? So what is the probability of this event? So probability of this event is largest number is 5. So other three numbers are which kind of number? Other these places, what are these numbers? These three numbers can be from 1 to 4 any number because largest number is 5. So this number should be less than 5. Right? So they can take the values from 1, 2, 3 or 4. Only these four values can take. Right? And these four numbers, these three balls will receive. How many ways it can be distributed? It is in 4C3 ways. It is possible in 4C3 ways because the largest number is 5. So among these four ball, one ball got 5 number, other three balls should get the number between 1 to 4. So there are four numbers possible. So it is 4C3 ways it can be distributed. Divided by total number of possible selections. So you have 20 balls in the urn and you have selected 4 balls from them. How many ways it can be done? Yes, we have discussed already in combination chapter. So it is 20C4 ways you can do. So therefore P of x equal to 5 is 4C3 divided by 20C4. Clear? So if x is equal to 5, we have got this one. Now you think what is P of x equal to I? So among this four ball, maximum number is I. So the other balls can take which values? It can take the numbers between 1, 2, 3 up to I minus 1. Correct? So you have three balls. These three balls will get 1, 2, 3, any number between I minus 1 to I minus 1. How many ways it is possible? Yes, it is I minus 1 C3 divided by, again 20 C4 ways is the total number. So P of x equal to I is I minus 1 C3 divided by 20 C4. I hope it is clear. So you can put any particular value I equal to 4, I equal to 5, I equal to 6. You can get its probability. I hope it is clear. Now look at this one we already discussed. P of x equal to I is I minus 1 C3 divided by 20 C4. Now what is P of x greater than 30? So you can do this in two ways because we know that random variables, all of their probability, if you calculate x equal to 4, x equal to 5, x equal to 20, it will give you the sum. So you can calculate 1 minus that event, or you can take it as P of x equal to 14 plus P of x equal to 15 plus dot 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 P of x equal to 20. Right? So this is basically the sum of I is equal to 14 to 20 P of x equal to I. But that part we already calculated. It is sum of I equal to 14 to 20 I minus 1 C3 divided by 20 C4. You can simplify this value and you can get this answer. Right? So this is the value as we discussed. Because again we have seen here that each of the events are mutually exclusive. So probability of their sum is their individual sum by axiom 3. Therefore we can get this value. Right? So these are some thing about random variable. Then we already discussed about the discrete random variable. And then few of the examples we discussed. and the contents we have taken from these references. I hope you like the video. I hope it is helpful. Kindly give your feedback in the comment box. We'll meet in the next video by defining probability mass function for a discrete type random variable. Right? Thank you very much.